we will have Christopher Hofmann from Chemnitz University. He's going to talk about simultaneous multi-parameter choice with application in inverse option pricing.
Thank you very much. Also, thank you very much to the organizers for having me. It is indeed my first time in Búzios, and I hope to return as soon as possible. So, what I'm going to present here is joint work with my PhD supervisor Bernd Hofmann, no relation, and Alois Pichler. So in the following, I'd first give a quick introduction to the setting we're dealing in, a very brief introduction to inverse problems. Then, define the forward operator and a few properties, and in the second part, give numerical examples and two heuristic parameter choice rules we have applied and implemented. Well, to point out a few relevant references. So, there we are. A few papers and results have been published by my research group before my days. Those George has mentioned in his talk as well Monday morning. And I'd like also to point out a few papers on heuristic parameter choice. The seminal paper by Hansen, which introduces the L-curve framework. The papers by Belger, which generalize these papers to or these ideas to a multi-dimensional setting, as well as the ideas by Naumova and Pereverziev, who deal with the choice of multiple regularization parameters. And this talk is based on this paper which we have submitted and it's waiting for publication. So, inverse problems, what are they? Usually we have some forward operator x, f, which maps from x to y, and the forward problem is to figure out y if we have x. So, the inverse problem would be we need to find x for observed y. Turns out usually it's not very easy, and the main problem is we might not have y, but only noisy observations y delta. And to overcome ill-posedness, we usually try to find stable approximate solutions x alpha delta, possibly by employing Tikhonov regularization, which is done by minimizing this functional. So we have noisy observations y delta here, some penalty term omega, as well as the regularization parameter alpha. So the big question in this problem is how to choose that regularization parameter. Unfortunately, there's lots of theory out there which gives us strong results if we have a deterministic noise model of this kind. In practice, we might either not have the noise level delta, or we might not know, or the noise might not even be deterministic. Therefore, we rely on heuristic parameter choice. And I'd like to introduce two rules which have been common knowledge. One is the L-curve, introduced by Hansen. So on a log-log scale, we plot the residue and residue here, or the residue norm, as well as the norm of the penalty term. And then this gives us, well, we do this for different regularization parameters, and it visualizes the trade-off between the residue and the penalty term. And the idea is to take this corner here, and that is the sweet spot, and we choose the appropriate or the according regularization parameter. And this is the idealized case from his paper for a linear forward operator. Another idea is the quasi-optimality rule. So we choose some series of alpha j's in this fashion given here. We compute x alpha j delta for all of these parameters, and then choose the parameter accordingly where this functional is minimized. So, in the following problem we're conducting, we're operating in the classical Black-Scholes model. Again, we're assuming the asset follows this Wiener process with this drift and volatility sigma, fixed strike, fixed asset price at time 0, and for our cases we limit ourselves to the unit interval, so time to maturities have been normalized. Then we define some time-dependent volatility functions, sigma squared or A, and auxiliary functions A, and some interest rate R, and it's also a auxiliary function capital R. This gives us then in turn the well-known Black-Scholes function or Black-Scholes function for these values and auxiliary functions. And using put call parity, we can then define or receive the corresponding call input values. Then, in the next step, we define the forward operator f, which maps these functions a and r onto these corresponding values. we assume that the functions a and r live in L2, and then define the space H with its corresponding norm. And the domain of the f is d of f. So what are the properties of this forward operator? First of all, injectivity. Under these conditions, or previously introduced conditions, that pair A of A and R in the domain of f is uniquely determined, and therefore we can simultaneously and uniquely identify that pair from observed option prices. Unfortunately, though, the forward operator f is locally ill-posed. So this means, or this justifies the necessity for regularization. And therefore we are employing a Tikhonov type approach of this type. So the idea is we have we have two penalty terms and two regularization parameters which we need to choose. Also, again, let me emphasize this forward operator is non-linear. And basically this is an unknown field in inverse problems, how to choose two regularization parameters at the same time. Also for a non-linear forward operator, and also with a non-deterministic noise model. And this particular application in inverse option pricing can serve as a benchmark or toy problem for this class of problems. So again, to motivate you and convince you that regularization is indeed necessary, I'd like to give a few numerical examples. So we're using Gaussian additive noise model, simulated data. We use some simulated functions, volatility, interest rate, discretization, and the time domain is 50, and some fixed strikes and core prices underlying. So if we have no noise, the whole situation is brilliant. No need for regularization. However, if we add 0.1% of noise, this gets a bit unpleasant. And the more we add, on the left-hand side is 1%, and the right-hand is 5%. This is, well, unbearable. To also convince you in the next step that, this looks beneficial, I'd like to give an example. So this is what inverse people do. At first one, you try and feather a bit around with these parameters and until your picture looks nice. And on the left-hand side, you can see that the total variation was used to regularize the volatility, and on the right-hand side, the second-order derivative was used. And these parameters have been chosen heuristically. So now we need to establish a parameter choice rule. The one I'd like to use or adapt in this case is the L hypersurface framework. This was introduced by Belger and is the generalization of the L curve. So we plot the residue Z against the regularization parameters omega 1 and 2 on a log-log scale and receive the generalized L hypersurface. If we do this numerically for these previous examples, again 5% noise here, second order derivative as a penalty term for both functions, this is what it looks like. So the idea is to find the sweet spot here which minimizes or which exemplifies this trade-off. So by just looking at it, this might be very unpleasant, and therefore we make use of the Gaussian curvature surface. So we plot the Gaussian curvature against the penalty terms on the left-hand side or the regularization parameters on the right-hand side. And in theory, if we pick the point with the highest curvature, that gives us our regularization parameters, and we can see the regularized solutions in the next slide. So again, if we consider it was 5% error, there was basically nothing there. This looks quite promising. So based on the approach by Naumova and Pervezev, I'd like to give or introduce another method we have implemented. So what they did is they used like a two-stage algorithm for a linear forward operator where they used quasi-optimality for every step. And from our previous examples, we know that the alpha is much easier to recover than beta. And we also have done substantial numerical calculations, and therefore we employ a combination of L curve and the quasi-optimality. So in the first step, what do? We choose the suitable sets of regularization parameters, Q and P. So Q here is the parameters alpha in this fashion, and P, again following the quasi-optimality in mind. So in the next step, we choose suitable alphas of beta j for all those beta j's in that set P, using the L-curve rule. And in the next step, we apply quasi-optimality to that series in order to determine beta. So again, the final step, we have to figure out or decide whether we apply this just to the interest rate or x, which is interest rate and volatility. Yeah, pleasantly enough, this is what we retain. This is the distinct shape of the L-curve for some fixed beta. And of course, I mean, the idea is to find this sweet spot here, the corner, and usually this is done by evaluating the curvature, or the Gaussian curvature. So this is what we do, and in all admissible parameters, or for all admissible parameters, the L-curve remains at this distinct shape. And even further, we receive alpha of beta j as one value for all betas in that admissible set. So in the next step, we apply quasi-optimality to that series. Again, the left one is to x as in volatility and interest, and the one on the right is just the interest rate. And we receive this shape and one unique minimum, and choose the next regularization parameter accordingly. Again, if we look at the regularized solutions, considering it was a 5% error, this is looks promising. So to convince you that this is feasible, I've done another example with a bit less error, different volatility functions, different interest rate, simulated data again, and we get alpha of beta j again, all the same, like 0.05 for all suitable beta j's, and we then again use quasi-optimality. This is with 1% noise, and the regularized solution looks much more promising in this example. So to conclude the talk, I'd like to give you a final or the first real data example to the previous method, or the previously introduced method on the L hypersurface. So this is a family of call and put options on the German DAX index. We got 24 observations, fixed strike K, and the underlying was, what was it, at 11.3 on that particular date. And yeah, we put this in, calculate the Gaussian curvature surface. It also looks very pleasant. And choose the regularization parameters accordingly. And this is what we receive. Well, for obvious reasons, we don't have the exact solutions yet, but at least this looks promising and realistic to me. And on the right-hand side, this is the observed and the predicted by Black-Scholes prices of that regularized solutions. So I'd like to conclude the talk with that and hope to be back next year.
Questions?
Two very quick questions. In this case, you can compare with the true interest rate, right? Because there is the interest rate in the risk neutral measure available from other sides. Or did you compare? I didn't read the graphs very carefully.
Sorry. As you know, there's like a whole theory in what should be the risk-free interest rate, right?
Yes.
So I wasn't exactly sure what to compare it to. And considering the levels is around 0, that makes a huge difference, right? So this is 0.2% and this is around 0.
I would compare with the prevailing interest rates on the bonds that on the market. I mean, during that period, that's how, at least, and also you can use that as a priori information anyway, right? So that. Oh, by the way, I was going to ask which a priori did you put?
What do you mean by a priori?
A priori information on when you do the regularization, yes. Somehow you have to incorporate a priori information on, or you are just using.
Oh, yeah, here you mean.
Oh, your regular. I see. Your regularization in both cases are just derivative types. It's not. You're not forcing it to be close to something.
No, it's derivatives.
Yeah.
We've tried total variation as well, but this has been very successful.
Yeah. No, I like total variation. I just think that somehow it's also important to put some expected value of the volatility or some kind of, just to give some behavior at infinity of the volatility or somehow. So that's just something that we learned by force that it was a good idea. But if you are getting good results, that's yeah. Okay, good. Thank you.
Thank you very much.
Just a quick follow-up. Basically, this question: you try something different from DAX, because DAX interest rate, because Germany was zero negative, Bund was very near zero, so it created a lot of problem, I think, to make a calibration if you use interest rate near zero. Did you try with other SPX?
Yeah, this is like the first real data example we've put in. So in the inverse problems community, you like to know the exact solution so you can have a convergence rate. So it was, the idea is to, so far again, as you're saying, we should probably do more real world examples.
Yeah.
But the line of thought was to study this kind of problem. And
I don't know, I just an idea. I think you have different kind of behavior if the interest rate near zero, like Germany and Japan, or real interest rate, like if in US now or Brazil, they're very high, you probably get different kind of behavior. This is just a guess.
Well, I'll certainly check this.
Any more questions? Okay, let's thank